So all we did is look at total energy to begin with, the energy at the end, set them equal to each other, got rid of stuff that we could get rid of, come up with an answer. Questions up to here, because I'm going to change one thing we did. All right, so here's the one change. I'm going to change my initial height. Now, and typically when I do this, students will go with the initial height is 30 meters, the final height's 10 meters. That's fine. Suppose I made this the initial height. Make this height is equal to 0 here. Sorry, final height. If the final height is 0, what's the initial height? In other words, what is that distance? So if I do the exact same thing as I did over here, that is now 20, that is now 0. So what I'm left with is 9.8 times 20. So I have 9.8 times 20 is equal to 1/2 V final squared. So that is not 2. That is 196 is equal to 1/2 VF squared. 392 is equal to VF squared. VF is 19.7879, something like that. Whatever I wrote down before. $7989. I get the same answer as I did before. So when you're doing these problems, you can make h is equal to 0 anywhere. Similar to, I can make my starting point anything I want it to be. I could make that my origin. I can make my origin anything I want it to be. So there's nothing special about the ground other than physically, if it hits the ground, then suddenly I've got non-conservative forces involved. But in this region right here, it's falling. It doesn't matter if it's falling from 30 meters to 10 meters or 20 meters to 0 meters or 50 meters to 30 meters. All that matters is it's falling 20 meters with just under its own weight. Because when we did the derivation, what we found was the change in the potential energy. So the actual value of the potential energy at any particular time, at any particular position, is not as important as the change in potential energy. There was a problem I gave on a test or quiz, master set, that's what it was. On a master set, where I had a box on a table and the box, let's say the table was 1 meter tall and the box is 1/2 meter tall and it's the ground. And I said, what's the potential energy of the box? And I gave the mass. And what assumptions did you make? So most of the people, actually I think everybody, chose the ground as h is equal to 0, which is an assumption. That's the assumption that you make. You assume you're on Earth, so G generically 9.8 meters per second squared. 2 assumptions. And then the height would be the height to technically the center of mass, so the height would be 1.25 meters. So if that's the assumption, then my potential energy is 5 times 9.8 times 1.25. So 49, 59 plus 2.25, 61.25, I think. Joules. But if you really didn't feel like doing much math, you could just say the center of the mass of the box is where I'm setting H is equal to 0, and the potential energy, 0 joules. Yeah, there was a 152 and 252 test. This is electricity and magnetism, where I gave a sphere and I said I gave a potential energy at the surface, and if you just plug straight into the normal formula, it comes out something completely different, but it boiled down to I can make zero, my potential energy 0 anywhere I want it to be. Questions to hear? All right, I go through a more extensive example. Should be a video for it, with the ski problem. So I will assume that you will watch that on your own. I do want to jump back, sort of combine the momentum and the energy stuff. We talked about collisions. And in the collision, assuming it's a closed system, in other words, the only two objects involved are these two objects. Momentum is conserved. So if closed system, momentum conserved. But occasionally I made a reference to a perfectly inelastic collision, and what will be called an imperfect collision. I know I've got a video on this, but I want to go over it as well. What type of collision it is depends upon the kinetic energy. If the change in the total kinetic energy is 0, give myself enough room there. So kinetic energy is conserved. We're not talking energy conservation, kinetic energy conservation. Naming system 1. We'd call this an elastic collision. These are elastic. Naming system number 2. Perfectly elastic. In the first naming convention, if K final is less than K initial, in other words, that we lose energy. So if we lose energy, and they don't stick, Under naming convention number 1, this is called inelastic. Under naming convention number 2, this is called elastic. And you can start to see some potential problems in this. If they stick together, naming convention number 1, this is perfectly inelastic. And naming convention number 2, it's inelastic. Unfortunately, some textbooks will go through one convention, some will do it another convention, and I just can't keep track of which book does which. So I came up with my own. I picked the ones which were unique So I do perfectly elastic if total kinetic energy is the same. I do perfectly inelastic. Let's see. So perfectly inelastic, and I use those two because we're talking the extremes. We have the maximum loss of kinetic energy, and it sticks together. No loss of kinetic energy. And then for this middle one, students suggested it, and I liked it. Imperfect. And there's one other category. Again, we're assuming a closed system. My final kinetic energy is greater than my initial kinetic energy. These we'll call it impossible. And sure, but I call this also Flubber-esque. If you've seen The Absent-Minded Professor, or I think there was one movie called Flubber, it's a reference to that. It's an object that when it bounced, it would gain kinetic energy, therefore it would bounce higher and higher and higher every time you bounced it. So if you're going to tutoring, at this point Mike Jones knows the way I do it. If you have some other tutor, or if you're looking at some other source, just be careful of they call it elastic or inelastic, which one are they talking about?
But what does that third one say? Counter.
This?
Sorry, like on the left.
On the left.
Yeah, like the kinetic energy of the third from.
Over here?
Yeah,
The third one?
yeah.
They stick together.
Okay.
So part C of your momentum lab, whatever that last part was. All right, any questions? All right, what's acceleration?
Change in velocity over change in time.
So, what does it mean for velocity? What happens if velocity changes? Or what are the three things that could happen for velocity to change?
The direction changes, speed changes.
Speed changes, I was thinking. Speed up or slow down. So yeah, speed changes or direction changes. Now in chapter 3, any math problem we dealt with in chapter 3, we were dealing with change of speed, but now let's deal with change in direction. This is chapter 8. So if I take stopper on a string, okay, let's secure it, and I spin this around my head, where do I need to let go so that I hit that spot? So let me stand here. If I spin this around, I'm not going to hit that. So if I spin it around, where do I need to let go so that I hit the X? So let's draw a model of what we're dealing with here. So here is the room, all right, that's the front board. There's the X. I think I'm standing somewhere about here and swinging this around kind of like that. So as far as communication goes, let's sort of deal like if this is a clock. So this would be 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, and then 2 o'clock, 1 o'clock, 2 o'clock, 4 o'clock, 5 o'clock, and so on. Speculation, where do I need to let go so that I hit the X?
6 o'clock.
Anyone else?
4.
No, the worst that happens is someone loses an eye. No, I've done this plenty of times. If I thought I might hit somebody, I will ask people to move. If you feel uncomfortable when I come to actually releasing it, feel free to move. If you move to somewhere where I'm pretty sure it's going to go, I will ask you to move again. And for the record, I did not hit Scott. I was doing something similar to this when I taught last time I taught middle school, and hopefully it is the last time I teach middle school. Scott was prone to exaggeration. Now I'll admit, I got closer to Scott than I intended, but I did not hit Scott. That was first period. Fourth period rolls around, student comes in and says, I understand you hit Scott this morning. No, did not hit Scott. So anyway, so 4 and 6. All right, let's see if that works. Let's see, I'm standing about here. I think we're good. I'm gonna do it more slowly because I need the control. If I do it really fast, then there's a little bit more inaccuracy in it. All right, so I want to release it when it is in this position. So 1, 2, 3. 6 o'clock didn't seem to work. All right, so 4 o'clock is next. And about here. So 4 o'clock would be, see that's 3, so 4 o'clock is about here, so facing Marissa. So 1, 2, 3, go. Any speculation about where I need to let go so that I hit the X?
2.
What'd you say?
2.
2? Now, if you say 159, I cannot differentiate that. I'm not that skilled. All right, let's see if Gaiman's right. I guess the idea was that it would keep perfect after I let go.
Yeah, that was my idea before.
All right. So 2 o'clock would put it about here. One, 2, 3. That's probably as close as I'm gonna get. So what happens as soon as I let go? Which direction does it go in? All right, so when I let go of here, which way did it go?
This one, to the left.
All right, when I let go here, which way did it go? Yeah, okay. This one like that.
Yeah.
This one went like that. It's going tangent to the path. It'd be helpful if I had drawn an actual circle there, but that's going this way, that was going, if I drew it properly, that way, that went that way. Because remember Newton's first law, an object will travel in a straight line unless something causes it not to. Also at a constant velocity. But as soon as I let go, oh yes, Grace.
Is that like, I forgot, inertia? Like if
Yes.
it's going like, okay.
Yes. Newton's first law, also known as the law of inertia. An object wants to keep doing whatever it is doing. As soon as I let go, what forces are acting on it as soon as I let go? The tension mounts. Think force diagram. We got F tau. As soon as I let go, is there friction? Tension. Other? No Jedi powers, there's no other there. Weight. All right, normal force. Has to touch something for normal force. So the only thing acting on it is the weight, which is which direction? Yeah, weight acts down. So that's why when I let go, it will curve downwards, but it's not going to curve left or right because there's nothing causing it to go left or right. So an object will travel in a straight line once I let go. So therefore, it naturally wants to keep doing what it's doing. So at any point, the velocity is pointing in the tangent to the curve. Let's see if I can actually draw more of a circle. Somewhere around there. So at this point, my velocity is traveling this way. At this point, my velocity is traveling this way. There, that's the direction of my velocity. That's the direction of my velocity. That's the direction of my velocity. So my direction is constantly changing, even if I'm going at a constant speed. So, since velocity is changing, since direction is changing, velocity changes. Since velocity changes, it has to be accelerating. Since it is accelerating, there must be a force, a total force. So as I'm swinging it, what is that force that's causing it to travel in a circle?
You.
I am an object, not a force in physics terms. I had it attached to the string as I was swinging it around. Wherever it was.
Tension.
Yes.